Well, it's a pleasure to see you all. What a great group. I'm so happy to be able to address you today and tell you a little bit about the things that we're up to with wastewater. So I'm going to be talking about energy positive wastewater treatment, whether that's possible, and if we can do it, what would be the quality of the water that we can get from that. So before I get into that, though, I want to introduce you to a new center at Stanford. It's the Codiga Resource Recovery Center. It was established last year. We've been working on a construction over on Sarah Street on the other side of campus, and the objective here is to build a pilot scale testing facility. It's unlike any other that I know about, where we can scalp wastewater off of Sarah Street sewer, and we pump it in, and we treat it through screens and then through an anaerobic process, which I'll talk about later. And then we have different qualities of water that can go to test beds where we can test mobile units. And so this is an exciting center, and we're going to be engaging a lot of different students in this activity. So in terms of how this operates, we have basic research that we need to scale up. And because at the bench scale, it's not meaningful, basically, until we get it to pilot scale with this kind of technology. And so we want to be meaningful. We want our research to have applications, so we're doing that. And we have Woods Institute, Renew It, as basic research as being funded through those mechanisms. And that gets us to bench scale. And then we need to move beyond that to full scale. And so there's a screening step. And the Codiga Resource Recovery Center comes in there as the vehicle for scaling things up. And then we want to get to the point where we have sustainable water cycles. Now, when I talk about sustainable water cycles, what I mean is cycles where we can get enough energy out through the residues that we remove from the water in order to power the cycle, to clean the water. Okay? So all those residues, those organic residues, are basically created by the sun, ultimately. And then you're basically taking that chemical energy and recovering it and then reusing it to clean the water. Okay? So that's the process I'm going to talk about here. Now, when we talk about conventional wastewater treatment, what happens is you separate wastewater into dissolved parts and the suspended parts. The suspended organics usually are settled out and then sent off to a digester to be digested anaerobically to produce methane. So we recover energy that way very often. What we don't always recover energy from is the soluble part of the dissolved organics. And then typically, in fact, what we do is we inject a lot of air in. And this air ends up creating a huge amount of microbial biomass that needs to be disposed of in some way. Huge amount. And it's energy intensive. As you can see here, kilowatt hour is needed for every kilogram of oxygen delivered. And we end up with a net energy consumption of 0.4 to 0.6 kilowatt hours per every cubic meter of wastewater that's treated. That's a big number, and actually it amounts to ultimately around 3% of the nation's energy load is basically due to wastewater treatment, and this is about half of that is for aeration. So the question is there some other way of handling those dissolved organics? What could we do? How could we get the energy out of the suspended or the dissolved fraction and not just the suspended fraction? And I point out here we get about 0.1 kilograms of solids per every cubic meter through digestion. So we can keep these numbers in mind, 0.4 to 0.6 kilowatt hours per cubic meter going in and 0.1 kilograms per cubic meter coming out. So if we look at the energy in the wastewater itself, there's actually quite a bit. Some of it is inert and can't be degraded biologically. Another fraction can. And if you take that amount and you combust it, you'd have 1.2 kilowatt hours per cubic meter. All right, and if you look at the suspended and dissolved, it's about 50-50. So about 0.6 kilowatt hour per cubic meter there available if we can harvest it in some way from each side. Okay, so it turns out that if we recover energy from the dissolved organics, the energy balance gets flipped. It gets flipped. Instead of now requiring energy input, now we have net energy out. And we've done the calculation and published an article on this. The net energy that can be produced could be as much as 0.25 kilowatt hours per cubic meter. In other words, now we're getting, before we were investing energy for the dissolved organics. Let's see if this works. Yep, it does. So before we're investing energy here, and the net result was 0.4 to 0.6 kilowatt hours per cubic meter in. And now we're talking about getting 0.14 kilowatt hour per cubic meter out as methane or as electricity. And then biogas here is also being produced. So if you sum those two, we end up with 0.25 kilowatt hour per cubic meter going out. That's what's possible if we can recover that energy. So recent pilot scale testing of a fluidized bed membrane bioreactor in Korea indicates that this is possible. And Professor Perry McCarty, that's the gentleman in the middle there, is an emeritus professor from Stanford who went there and for several years in Inha University was a resident researcher, and basically led a group that developed this technology. And we will be testing it for the first time at the Kodaga Resource Recovery Center in the United States, I should say. First time in the United States. It was developed in Korea. So dissolved organic matter converted to methane, and then with combined heat and power converted to electricity, and that can drive, that can be through an engine. Okay, so this is a seminal paper describing that process that they just published. Now, what's exciting about this is that performance is excellent, even at low temperatures. And in the past, we've always thought that it was impossible to treat wastewater at low temperatures and get efficient removal of the organic matter. All the research to date had been basically said that was impossible. But with this system, for reasons I don't have time to go into very much right now, we're able to, you actually have a small footprint, high quality effluent. That's the key thing. It meets the standards for wastewater treatment. Low solids production, much lower than what you're talking about with aerobic systems. And overall recovery of electrical energy is about 32%. And this level of energy would enable net energy zero wastewater treatment. So this is a system. You have little activated carbon beds where the fluidized by upflow of water. And some of them have membranes in them, and we can suck the water out after it's been cleaned and up by the microbes. Okay? So it turns out that with this process, there's additional heat, and there's also small amount of biosolids produced. And what that means is that when you have a small amount of biosolids, you can dewater it, and say you get it to 85% water, 15% solids. And now because you have so much more energy, so much more heat, you can potentially completely dry out the solids, which was never possible before. And so you can take that heat, and so we get the electricity, which I already described, we get that heat, we can now make steam and dry out these solids. When these solids are all dried out, now they can be combusted, and you can create syngas. And so we end up with much less biosolids. We go from 100 down to 10 grams of ash. Okay, so 90% reduction in the solids that need to be carted off and managed somewhere. And then another 0.1 kilowatt hour per cubic meter can come from the syngas that's through a gasification of those solids. So now we add the total. We have 0.25 plus 0.1. We're now at 0.35 kilowatt hour per cubic meter out. Okay, so when you're done with this, nitrogen's still in the wastewater. You say, well, that could be bad. Well, it could be bad. If you're discharging to the environment, it would cause problems. But if you look at it for agriculture, it's perfect. Because now we can replace the Haber-Bosch process, which is a very energy-intensive process needed to produce ammonia. And here we can use the waste nitrogen right away for agricultural applications, as shown here. Now, if you do need to get rid of the nitrogen, which is often the case on the coastal regions, we can't recycle all the water. And so then it turns out that it's really critical that we remove that through some means that doesn't take so much energy. And basically, the Water Environment Research Foundation said nutrient removal is the most pressing water quality challenges currently facing utilities all over the world. And that's because of these dead zones, 400 dead zones in regions all around coastal regions all around the world. So it turns out that the nitrogen fraction of wastewater also has energy in it. And you can quantify that. It's about 0.3 kilowatt hour per cubic meter. And that's this little segment right here. So can we recover that? And this goes back to some years ago. This is Yanif Sherson here. He came to me as a PhD student, and he said, well, we're making rockets with nitrous oxide. We're making rockets. And I'd always thought of nitrous oxide as a terrible greenhouse gas that we wanted to not make. But he wanted to make nitrous oxide from waste nitrogen. So we began a collaboration, and it was successful. We were able to actually produce nitrous oxide. Here's the energy from nitrous oxide decomposition. Here's, if you use methane as a fuel, you can use nitrous oxide as an oxidant. And it's a very powerful oxidant, more powerful than oxygen, and get more energy out using nitrous. So basically, rocket fuel or methane oxidation, both are possible if we can recover it. And so you need to take ammonia in wastewater, convert it to nitrous oxide, and we go through a nitrite intermediate, and then we use a special process, the can-do process, we call it. Better than can't do, and then it goes into combustion. And so here's where we would use it to oxidize the biogas and recover additional energy. We've tested this at a 650 kilowatt engine in Redwood City wastewater treatment plant, just a little north of here. So overall, the performance looks like this: about 75% conversion of the nitrogen to nitrous, and 95% nitrogen removal overall in these 2 steps of this process. And so we're now working on commercializing and upscaling this system, and we have a system running at Delta Diablo that we've been testing there, and that's a wastewater treatment plant in the North Bay where we have a system set up to test. Now we've now taken the carbon out, the organics out, we've taken the nitrogen out. There's still another opportunity to do something with more energy recovery, and that is because, at least on plants that are near the ocean, when you discharge that wastewater, it's almost fresh. It's almost fresh water. And if you discharge it to the ocean, the ocean is very, very saline, and it turns out the difference in salinity between the wastewater and the ocean is such that you could potentially recover energy from that. And we have a system for doing that. We've been testing, and there's essentially lost energy of 0.6 kilowatt hour per cubic meter if you just let it discharge. So what can you do? Well, it turns out that there's these low-cost salt gradient batteries that appear capable of recovering 70% of that energy. So about 0.4 kilowatt hour per cubic meter. Okay? So if we look to the future, what could it bring? So we have seawater. If you do seawater desalination, just for metrics for you to keep in mind, it's about 3 or even up to 4 kilowatt hour per cubic meter to push the fresh water out of seawater. 3 to 4. If you talk about conventional wastewater treatment, if you take the nitrogen out, the organics out, and the salt out, it's 1.4 kilowatt hour per cubic meter. If you talk about the new processes, we're talking about where we can reduce the we can basically flip the organics over to the energy production side, and the nitrogen is reduced, the energy for nitrogen removal is reduced, and we see a little improvement in this desalination. We could get to energy neutral wastewater treatment. Now, if you talk about a coastal region, then we call it the blue energy. That's the salt gradient energy I described. It could potentially recover, say, half of that 0.4 kilowatt hour per cubic meter through when it's discharged to the wastewater or discharged to the ocean. So we might be talking about 0.2 kilowatt hour per cubic meter in a coastal system. So I just wanted to say, acknowledge our research group, all the people who've made this possible. This was a day when 2 people weren't there, so I've added them in, who played an important role with the can-do process. And then this is what's coming, not really, but this is the cartoon version of what's coming, showing the mobile units, one that does everything, including watering the Stanford tree, which sorely needs it, and even a data center, which people wonder how you could illustrate cooling of a data center. And I have to say, the artist who did this, Larry Gonick, is amazing and can do those kind of things that I could never do. Okay, and so that's it. That's all I have, and thank you very much. There's a comment question here. Yeah.
Where do you see this really being
Okay, so the questions are 2. There's mobile units. How do we see that being applied? And also developing world, right? So the mobile units, we see those as a way of facilitating rapid scale-up of these systems, right? And we want to do that in parallel, and also to help overcome basically reluctance to adopt new technology. That's the goal, and accelerate that process. They are at a scale that they might be used for some decentralized wastewater treatment applications, satellite treatment. They could be used at that scale. Say, for example, golf courses or something like that. Okay, so that's one example. And then on the developing and developed world, of course, the developed world, we have all this existing infrastructure. And we have to see how do things plug into that. Having mobile units helps with that, understanding what could plug in where, and also giving comfort level to the utilities. So we have to think about that aspect. When we go to the developing world, satellite treatment systems or decentralized systems may make more sense than putting in massive infrastructure for sewage collection and so on. So there's opportunities in both areas. Yeah. Yes. Okay. Okay, that's a great question. So the question is, how do we finance this? Well, right now what we're doing is we have some initial money from a gift, from a donor, okay, that helped us build this center, along with funds from the university itself. So that will help us get things started. And then we're targeting both utilities for some support for mobile units, and then also thinking about companies that would sponsor research as well. And we do plan some proposals to foundations. So there's a bunch of things that are ongoing. It's not an easy problem. It's something that takes a lot of effort to do. Yes. Mm-hmm. Okay. Yeah. Okay, got it. So the question is that how do we deal with the fact that there's different situations all around the world, and you have different temperature, different humidities, and you need to be able to accommodate that. Well, the truth is, when you're dealing with biological processes, warmer is better. Right? So I'm not so worried about the warm places as I am the cold places. That's why when this system, the Korean system, worked all the way through the winter, that was very persuasive for me, because that was the critical moment when we knew, okay, this is a technology we really need to push hard, is when it worked during the winter months. Yeah. So I think it will be adaptable, and they're testing it in Singapore right now. China or Taiwan would be testing it and moving it to full scale pretty soon, I think. And so there's a lot of groups that are pushing, and we're the first in the US. Yes. Yeah, so the question is about sour gas or other things that might be in the gas, right? Siloxanes. Okay, there's different things that can be in the biogas. And so that is something we have to look at. In each case, it's going to depend on what's in the wastewater. If you have a lot of sulfate in the wastewater, that could produce a lot of hydrogen sulfide. There's just a sour gas, which you mentioned. So you have to look at the source of the water, what the quality of the water is. Now, there's ways to deal with hydrogen sulfide. We can add some metals, and then we can remove the sulfide, but then there's additional costs associated with that and issues associated with that.
So would you do that upstream before you start the process?
You can add metals upstream, and then they can go into the reactor and produce, for example, iron sulfides, which would drop out. Yeah. But that would impact the process for sure. Yeah. Mm-hmm. Yes.
All right. Another question. Can you go into more detail about the seawater, freshwater, and energy creation?
Yeah. So we have a salinity. This is work originally developed by Yi Shui's group in material science. And they developed this thing called the mixing entropy battery, they call it. And then we thought, well, we can use this for wastewater treatment. And so then our group started working with their group, and we started testing this thing. And at first, we were using very impractical electrodes. But now we're using very cheap electrodes. Okay, I have 5 minutes, thanks, Lee. We have very cheap electrodes now. In fact, one of the electrodes is Prussian blue. So Prussian blue, some of you are wearing Prussian blue. Right now, you're wearing Prussian blue. Prussian blue is on your blue jeans, right? And so we can use that material that dyes the blue jeans. It will actually change redox state, okay, when you use it as an electrode. It goes from one state to another, okay, depending on whether it's accepting or giving up electrons, okay. It can toggle back and forth. And then there's another electrode which we use, which is it's called PPY. It's an organic polymer. And this material can also toggle back and forth. So one toggles back and forth in redox state when sodium enters it or leaves it. The other one toggles back and forth when chloride enters or leaves it. So what happens is when you put fresh seawater in, the sodium ions go one direction into the one electrode, the Prussian blue, and the chloride ions go rushing into the other electrode, the PPY. And the current goes the direction of the sodium, right? Positive, right? So the current's going that direction. Now all of a sudden, when you stop that flushing with seawater, and now you flush with fresh water, guess what happens? The current reverses direction. And you get power on both strokes. Okay? Boom, boom. Okay, just like that. That's what happens. And so we think this is a pretty promising technology. Yeah. Of course, there's issues. Things like biofouling, and the power density isn't not that high. But, we're talking about a system where this can be managed when you put it at the end of a wastewater treatment plant. Yeah. Mm-hmm.
What's the order of magnitude of cost for these mobile units and capacity units?
Yeah, so the mobile units, we're in the range for outfitting them fully and remote monitoring and control around $300,000, something like that. Yeah, to have the whole thing fully equipped. Yeah.
Sorry, but what capacity?
Pardon me?
But what sort of capacity?
What sort of capacity? Well, we're shooting for, it's like on the order of a gallon per minute, something like that. Mm-hmm. Okay, how much? Okay, one last question. No more time except now. Okay, go ahead. The point is, why would we want to do this, right? That's the point. Why would we want to get energy from the saltwater freshwater gradient? Well, the reality is when you have a treatment plant on the coast, they're usually at the lowest place in town. And if you're going to recycle all the water, you would have to pump it all the way back up and have users everywhere up, right? Do you see what I'm saying? And so you can't practically do that. The energy is prohibitive to do that. And so it's better to discharge. Now, if you discharge, then why not recover something from it rather than waste the energy completely? Yeah. Is that it? Okay, one more? Okay.
I know some exhaust gas from internal engines.
Yes.
Working, and you cleaner than the air around us. The water treated by this process be cleaner than the water from nature, such as stream or river?
Yeah, so that's a great question. So if we do the safe MPR process, that process that I described, you get the organics out. There's still the nitrogen in there. That's dirty, right? But no, it could be useful. In that form, it's fertilizer, and you could use it on agriculture. Okay, now if we do need to take it out, say in a coastal environment, there's a way to do that and recover some energy, as I pointed out, right? And then if you want to take the salt out, you can do that too. And so it can get very pure water when you take the salt out. It's like reverse osmosis of seawater, only for no energy investment. Yeah, okay? Okay.
Okay, well, thank you.
Thank you.